first thing we want to do is take a look at this energy drink. And we want to just make some observations about the drink and the nutrition label. So just take a look at it. What do you observe? As you make those observations, take a look at some of the numbers. Take a look at some of the ingredients. Do you recognize any? Are there any you're not sure about? As you continue to make these observations, think about things you might wonder about, questions that come to your mind. Like, why is there no fat? Or why is there sodium in an energy drink? And then make some predictions. Is this a healthy energy drink because it has vitamin C? Is it unhealthy because it doesn't have any fiber? And make some predictions about it. So take a minute, write down some things that you observe, some things you wonder, some things you predict. One of the questions that we're going to be spending a lot of time analyzing is just that. Do energy drinks provide a source of energy? So we're going to be looking at chemistry in light of this idea of energy drinks and how it relates to health. So let's start with the 6 basic nutrients. Now, some of these nutrients are going to provide calories. Some will not. The nutrients that do not provide any calories are water, vitamins, and minerals. The nutrients that do provide calories are carbohydrates, lipids, and proteins. That raises another question. That question is, what's a calorie? A calorie is just a way that we can measure energy. It's a unit of energy. We find calories in the foods we eat. So you might pick up a Snickers bar and it says 250 calories. This is a measure of how much energy that Snickers bar can give you. Now the problem is, if we don't use that energy, we store it as fat. So how do we get energy from food? Well, that's the process of digestion. As we take food into our body, there's a series of chemical reactions that are going to break that food down and release that energy in the form of calories. Take a minute, write a statement that proves you know what calories are. Pause the video, write it down. Energy is found in chemical bonds. So whenever these atoms join together to make molecules, they form chemical bonds. Those chemical bonds then provide energy as they're broken. So what I have here is an example of a chemical reaction. Glucose, which is just sugar, combined with oxygen, after a chemical reaction, makes carbon dioxide, water, and then we get this release of energy. In this case, it's in the form of a molecule called ATP. We can break that molecule down very easily to get energy. Reactants are anything that's on the left-hand side of that equation, glucose and oxygen. The products are anything that's on the right-hand side of that equation, carbon dioxide and water. The coefficients are the big numbers that are written in front of the molecules or atoms. So in this case, 6O2 or 6CO2. That 6 is a coefficient. The C stands for carbon, the O stands for oxygen. The little subscript tells us how many atoms of that element are present. Chemically, we're taking glucose and we're taking oxygen. Through this chemical reaction, we're going to rearrange those atoms, break chemical bonds, and form new ones. Breaking those chemical bonds is going to be the thing that releases energy. So we can balance equations because we're not losing carbon, we're not losing oxygen in those reactions, we're just rearranging them. So in this case, to balance an equation means the reactants need to equal the products. If I have 2 atoms of hydrogen on the reactant side, I need to have 2 atoms of hydrogen on the product side. So take a look at that first equation, and sure enough, I have 2 atoms of hydrogen on the reactant side, I have 2 on the product side. But when it comes to oxygen atoms, I have 2 on the reactants, but I only have 1 on the. One of the things I can do is I can add a coefficient. What I cannot do is add a subscript. All right? Because matter is neither created nor destroyed, so I can't go adding atoms in there. But I can add molecules to the reaction. So in this case, if I add a 2 in this place, What that means is now I have 2 molecules of water. So that's 2 times 2 for hydrogen. That means 4 hydrogens. And then 2 times 1 for oxygen, that's 2 oxygens. Now if I go back over here, I'll notice I only have 2 hydrogens and 2 oxygens. But now I need 4 hydrogens. So I'm just going to add a coefficient here. So I have 2 times 2, 4 hydrogens, 1 times 2, 2 oxygens, and it will be a balanced equation. You work on the second one down there for a minute, pause the video, and work on that. See if you can figure out how to balance that chemical equation. So what I'm going to do here is try to balance this equation. I have 4 hydrogens on this side, only 2 on this side. So if I add a 2 here, that will give me 4 hydrogens. But notice that it also gives me 2 oxygens. Well, I have 2 oxygens here also. All right, so that gives me a total of 4 oxygens. If I go back to this side, I only have 2 oxygens, so if I just add a 2 here, that gives me 4 oxygens. So 1 carbon, 1 carbon. 4 oxygens, 2 plus 2, 4 oxygens. 4 hydrogens, 2 times 2, 4 hydrogens. Remember that molecule ATP? Well, this is what ATP looks like. Ribose is a sugar, adenine is a nitrogen base, and then I've got these 3 phosphates that are joined together by chemical bonds. You'll notice that there's some stored energy between the second and the third phosphates. That's where most of the energy is stored. There's also some energy stored between the first and second phosphate, but generally we just use the ones between the second and third. Whenever we break that chemical bond, energy gets released. Then we can just recycle that ATP, adenosine triphosphate. We can add another phosphate. After we take the one off, we can add it back when we get some more energy, and we can reuse it, kind of like a rechargeable battery. We use energy for all kinds of things, but sometimes chemical reactions can't happen unless we add energy. That's called activation energy, whenever there's energy required for a chemical reaction to occur. So you'll notice in my little graph here, I've got some reactants. These reactants can't come together. We can't make that chemical bond unless we have all this energy that we need. We can get that energy, but sometimes it's just not available. There's proteins that are called enzymes. Enzymes help lower activation energy. In other words, they just make reactions easier to happen. So the reaction is easier because there's a presence of an enzyme. Think of it kind of like a tool. Enzymes are kind of like tools. Tools just make jobs easier. You have the right tool, the job is a lot easier. Now, you could do the job with a different tool, it just won't work very well. Or without the tool, it won't work very well. But you have the right tool, it can really make the job go well. In case of activation energy, sometimes the reactions can't happen without the presence of an enzyme. Once the enzyme is present, the job just goes much easier. It's much faster. The activation energy is lowered. So some types of reactions are going to require some energy. We call those endothermic because the energy is going in. And that's what I have illustrated in the top. So I've got some chemicals. To get those chemicals to join together and form bonds, endothermic. Energy is required. Other reactions are exothermic, that is, energy is given off. So here we break the chemical bonds in the second example, and energy is released in that case. So what I have is some vinegar plus baking soda. So in this reaction of adding vinegar and baking soda, I'm going to get some products. One of those products is carbon dioxide will be given off, as well as some water. If I add more reactant, then I would expect more product. But what if I add a lot more vinegar, I just don't add a lot more baking soda? Well, at some point, the baking soda is going to be used up, and the extra vinegar is not going to have anything to react with. This is going to be an exothermic kind of reaction. That is, I add the vinegar and the baking soda, and I'm going to get a reaction, and it's going to give off carbon dioxide and water as a result.